Have you ever noticed how a compass needle twitches when placed near an electric wire carrying current? This simple yet fascinating observation takes us into the world where electricity and magnetism unite. When charges move, say, electrons in a wire, they don't just power your devices, they also create invisible magnetic fields around them. This was brilliantly demonstrated by Hans Christian Ørsted, who observed that a magnetic compass responds to electric current. It's a discovery that changed physics forever. Just like a magnet, a current-carrying wire forms magnetic fields. In fact, the pattern around a straight wire looks like concentric circles. And when current flows through a circular loop, it creates a field resembling that of a tiny bar magnet. These magnetic fields aren't just curiosities, they govern the working of countless devices we use every day, from electric motors to magnetic sensors. Now let's dive deeper. How do we actually calculate the magnetic field from a piece of wire carrying current? That's where the Biot-Savart law comes in. This law allows us to determine the magnetic field at any point in space due to a small current-carrying segment, what we call a current element. Here's the formula: dB equals mu naught divided by 4 pi multiplied by IDL cross R hat divided by R squared. In this expression, dl is the small vector element of the wire, R hat is a unit vector from the wire to the observation point, and R is the distance between them. The direction of dB is perpendicular to both dl and R following the cross product rule. And mu naught, the permeability of free space, has a value of 4 pi into 10 to the power minus 7 Tesla meter per ampere. This law is key to understanding magnetic fields around wires, loops, and solenoids and forms the backbone of magnetostatics. Let's pause for a moment and appreciate the vector nature of this law. Because magnetic fields are vectors, we need to consider not just their magnitude but also their direction. The cross product between the current element and the position vector ensures that dB is always perpendicular to both. The size of the magnetic field depends on the sign of the angle between them. It's maximum when that angle is 90 degrees. Want to get the direction right? Use the right-hand rule, point your thumb along the current, fingers toward the observation point, and your palm gives the direction of dB. Visualizing this is crucial, especially in complex situations like current loops or curved conductors, where symmetry and vector addition become powerful tools. Let's now apply the Biot-Savart law to a simple and symmetrical setup, a circular current loop. Imagine a loop of radius r, carrying a steady current I. Each infinitesimal segment of current contributes a tiny magnetic field at the center. Because of perfect symmetry, these tiny vectors all point in the same direction along the axis perpendicular to the loop. When we integrate over the full loop, the formula becomes d equals mu naught multiplied by I divided by 2r. This means that the magnetic field strength at the center increases with current and decreases with radius. This setup is the basis for devices like Helmholtz coils and magnetic field sensors, and it all begins with this neat application of the Biot-Savart law. Now let's derive something a bit more involved: the magnetic field at a point on the axis of a circular loop. Suppose the point is at a distance x from the center along the axis. Here too, symmetry is our friend. The horizontal components of the field cancel out and only vertical components add up. After applying the Biot-Savart law and integrating, we arrive at B equals mu naught multiplied by I multiplied by R squared divided by 2 into open bracket R squared plus x squared close bracket to the power 3 by 2. That's a powerful expression. It tells us how the field decreases as we move away from the center and gives us the exact value at any point along the axis. This formula is widely used in designing magnetic coils for experiments speakers, and MRI machines. Let's now work through a quick example together. Suppose we have a circular loop of radius 10 centimeters carrying a current of 5 amperes. We want to calculate the magnetic field at the center of this loop. The formula is B equals mu naught times I divided by 2R. Here, mu naught is the permeability of free space equal to 4 pi times 10 to the power minus 7. The current I is 5 amperes. The radius R is 0.1 meters. Now, substituting the values, we get B equals 4 pi times 10 to the power minus 7 multiplied by 5 divided by 2 times 0.1. Simplifying, B equals to pi times 10 to the power minus 6 divided by 0.1. That gives B equals to pi times 10 to the power minus 5 Tesla. Numerically, that is approximately 6.28 times 10 to the power minus 5 Tesla. Even though this value looks small, such a magnetic field is very important in the working of galvanometers and other precision instruments. Let's quickly revise what we've learned. The Biot-Savart law allows us to calculate the magnetic field produced by tiny segments of current. It's a vector law, which means direction is as important as magnitude. We use this law to find the field at the center of a loop and on its axis, results that are foundational in electromagnetism. This topic isn't just theoretical, it forms the base of technologies like magnetic resonance imaging, particle accelerators, and even wireless chargers. I hope this session helped you visualize how moving charges shape the magnetic space around them. In our next class, we'll build upon this and explore Ampere's law and magnetic field lines in more depth. Until then, stay curious and keep questioning how the invisible forces of nature are shaping your world.